I'm Mirum Famay and welcome to my lecture series on computer and network security. In this third part on authentication and access control, I will talk about firewalls, which are a specific method to ensure only authorized traffic enters and leaves a computer network. And here you can see the general model of a firewall. Specifically, the firewall stands between an internal protected network, for example, an enterprise network of a company, and an external untrusted network, such as, for example, the internet. And the firewall has several design goals, 3 to be specific. First of all traffic that comes in or goes out of the network must pass through this firewall, so it can be inspected and the firewall can decide whether or not to let it through. Second, only the authorized traffic is allowed to pass through the firewall. And third, the firewall should be immune to penetration. As such, it should make use of secure hardware and software. And the firewall can use various properties of the traffic to decide whether or not to allow it. For example, it can look at the source or destination IP address, at the transport layer port numbers, at the application protocol that's being used, at the identity of the user, or the type of network activity. For example, it can try to detect denial of service or scanning attacks. Firewalls can be categorized based on at what level in the network protocol stack they perform their filtering and inspection. And 4 main categories exist. The first one is the packet filtering firewall. This is the simplest type of firewall, and it provides a network access control for each packet separately at the transport layer, and then forwards or discards these packets. The stateful inspection firewall is similar to the packet filtering firewall, but keeps track of outbound TCP connections. As such, it only needs to keep the TCP ports active of the currently active TCP connections and can more easily detect TCP traffic bound to invalid ports. The third one is the application proxy. This is a much more complicated type of firewall that will terminate all TCP connections and then inspect the traffic at the application level. As such, it performs deep packet inspection. It can authenticate users and only allow traffic for authenticated users. Finally, the circuit level proxy is similar to the application proxy. It also terminates TCP connections, but it examines the content only at connection establishment, and after that it doesn't perform any more deep packet inspection on the actual packets of active connections. The first type was the packet filtering firewall, and let's take a closer look at how it works. As I mentioned, it works at the transport layer, and it can use information in the transport header, the IP header, and the network header of a packet. The main information that is used are IP, source and destination address, the IP header fields, and the transport layer information such as the TCP port. Such a packet filtering firewall will usually define a set of rules that either allow or disallow traffic with certain values for these header fields. And there are 2 main types of default behavior. First one is whitelisting, where packets are discarded by default. That means the rules specify which packets should be allowed to pass through the firewall. The second type is blacklisting, where packets are forwarded by default. This means that in this case, the rules are used to determine which packets should be discarded. A whitelisting firewall is obviously more secure, as specific rules need to be defined before traffic is allowed. However, blacklisting is easier because, for example, if a new type of service is enabled on a network, a whitelisting will first require the firewall to be reconfigured before the service can be used, while blacklisting will automatically allow it to be used. And here you see an example of a rule set for a packet filtering firewall that only allows in and outbound SMTP traffic. SMTP service usually uses port number 25, so that's also what this firewall rules assume. And as you can see in the first rule, it allows TCP traffic coming to port 25, so incoming SMTP traffic. However, the SMTP traffic coming through port 25 in the internal network will originate from an external port that is above 1023. So here we need to allow all traffic outbound to an external address using a port number above 1023. Inversely, rules C and D allow outgoing traffic to some SMTP service running outside of the network. However, the internal port on the internal host connecting to the external port 25 will be any random port above 1024. As such, this configuration has some problems because rule D would allow any incoming TCP traffic on a port above 1023, which is obviously not what we want. And I have a question for you related to this firewall configuration. How can we solve this problem and no longer allow any TCP traffic besides SMTP? Potential answer A is to remove rule D. Answer B is to add a source port field to each rule. Right now the rules only have a destination port field. C, we can add a source port field and on top of that add a flag whether or not the traffic is a TCP acknowledgement to each of the rules. And D, none of the three solutions actually provide a solution. So take your time to think about it and pause the video if you want. And let's take a look at what is the correct answer. The correct answer is option C. Option A is not a proper solution because if we remove rule D, all outgoing SMTP traffic would also be blocked, which is not what we want. And if we remove rule, if we add only a source port field, an attacker can still use port 25 for other things. Even if port 25 is supposed to be reserved for SMTP, nothing will actually forbid an attacker to use this port for other kinds of services and goals. And here you can see the solution for rule D, where we have added a source port number and also an acknowledgement flag. So you can see that now we've included that traffic that is coming into the network with a destination port above 1023 needs to come from port 25 on the source. Obviously, this would not stop an attacker from running another service on TCP port 25, but we also specify that only acknowledgements are allowed. So that means that only TCP traffic that serves as an acknowledgement to another TCP packet that was sent before can come into the network now. And to see if you understand how these packet filtering rules actually work, I have another question for you. So given these 5 rules, A, B, C, and D, and E, which of these 4 packets, 1, 2, 3, and 4, would be permitted by the firewall? So which of them would be allowed to pass through the firewall? Here you can assume that the address 172.16.1.1 is an internal one, and 192.168.3.4 is an external one. Feel free to think about this and pause the video. And let's take a look at the correct answer. The correct answer is that all 4 packets would actually be allowed to pass through, because all of them satisfy one of the first 4 rules. For example, if you look at packet 1, it matches the first rule, so rule A, because it is incoming, it comes from an external address, goes to an internal IP address, uses a TCP protocol, and has destination port 25. As such, it will be permitted. Similarly, the other 3 packets will also be permitted to enter the network. Let's take a look at some attacks that are used against packet filtering firewalls. The first one is IP address spoofing. In this case, an attacker will use a fake address as a source IP address of the packet. This is usually not checked, so an attacker could, for example, use an internal source IP address to make the firewall think that the traffic actually comes from the internal network. This can, however, be addressed, mitigated, by dropping all packets that enter the firewall on an external interface. This is a network interface that comes from the external network, such as the internet, but has an internal IP source address. By checking this, the firewall can ensure that spoofed packets will not be allowed into the network. The second one is a source routing attack. Source routing information can be added to IP packets to tell the network, for example the internet, how to route packets from the source to the destination as hints. This could be used by an attacker to confuse the firewall into thinking the packet comes from somewhere else. This can also be mitigated by dropping packets that use this source routing option in the IP header. The final attack consists of fragmenting the IP packet into tiny fragments so that the TCP header does not fit into the first full fragment. This can trick the firewall into only inspecting the first fragment of the packet and not having all necessary information and still allow the packet in even if it shouldn't be. Mitigation strategy is to drop all packets that do not contain at least the required header information in the first fragment. As I showed, there are some issues with packet filtering firewalls, as outbound TCP connections usually use a random port number above 1023 to bind on in the local network. This means that a packet filtering firewall, as it does not maintain information about these outbound TCP connections, needs to allow all incoming traffic on any port number above 1023 to make sure it doesn't block any traffic of an existing TCP connection. This can be solved with a stateful inspection firewall. Such a firewall keeps track of all outbound TCP connections. As such, it also knows on which local port they are bound and can only allow incoming traffic on ports above 1023 that actually is destined for one of the ports of currently open TCP connections. This greatly improves security of the firewall. Application-level gateways or proxies will actually act as relays of application-level traffic. They break TCP connections, then inspect the application-level packets inside and set up a new TCP connection on the other side to relay the traffic. Therefore, they allow, for example, authentication, where a user first needs to authenticate, for example, with a username and password, before its traffic will be allowed to pass through the proxy. It can also be used for more advanced filtering services, such as only allowing certain functionality of applications by doing deep packet inspection. The problem with this type of firewall is, of course, that it requires a lot of computational power, as the application packets need to be inspected. And also there are privacy concerns related to looking at the actual application traffic of users. The fourth and final type of firewall is a circuit level proxy. It is similar to the application level proxy in the sense that it also terminates TCP connections. It can also use authentication before deciding whether or not to relay this TCP traffic between the internal and the external network. However, in contrast to the application level proxy, it does not operate at the application layer and will not perform deep packet inspection. It will only intercept the first packets of a TCP connection while it's being set up, then decide whether or not to allow this connection, and once it's been allowed, it will just relay all the packets. As such, it is less processing overhead than an application layer proxy, as it's only doing computations when the connections are being set up. Large-scale modern enterprise networks are usually split into different parts, and they contain a so-called demilitarized zone, or DMZ. This DMZ contains servers that need to be externally accessible, for example, through the internet. This could be a web server, an email server, DNS server, VPN server, and so on. As such, these networks have multiple firewalls. The first one is the external firewall. It provides basic protection to the DMZ and the internal network. At this stage, no in-depth protection can be provided, as some traffic still needs to be allowed to pass through for external users to be able to, for example, view the web page, or for employees to check their email from home. The second, internal firewall, adds more stringent filtering to limit the outside access to the internal network. In this case, nearly no traffic should be able to enter the network except if it's traffic related to a TCP connection that was opened from inside the network. Also, the internal firewall protects the internal network from the DMZ and the other way around. For example, the DMZ, as it's less protected, is more vulnerable to attacks, and therefore if one of the servers in the DMZ is infected by a virus or entered by an attacker, the internal network is still protected. Also, the other way around, an attacker could operate from inside the internal network and try to access the DMZ servers. And this ends the video on firewalls. In the next video, I will continue to talk about access control and focus on intrusion detection.